Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the ancient dance of Earth's first continents. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. 4 billion years ago, Earth wears no armor. The planet's surface exists as a thin, restless skin stretched over an ocean of molten rock, and nothing solid endures for more than a few million years at a time. Where continents will one day stand, there is only the endless churning of magma and the brief, violent emergence of volcanic peaks that crumble almost as quickly as they rise. This is the Hadean Aeon, named for the ancient Greek underworld, a time when the boundary between solid and liquid remains negotiable, temporary, subject to revision without notice. The early atmosphere hangs thick with water vapor and carbon dioxide, a greenhouse blanket that keeps surface temperatures hovering near 400 degrees Celsius, hot enough to melt lead, yet still cool enough for the first experiments in crustal formation. Beneath this steamy shroud, the planet's surface attempts permanence like a child building sandcastles at the water's edge. The differentiation of Earth's interior continues its patient work, a process so fundamental that it will determine the chemical composition of every rock that will ever form. Iron sinks toward the core with the determination of gravity. Lighter silicate minerals float upward like cream rising in cosmic milk, and the chemical ingredients for future continents begin their slow, inexorable separation. The first attempts at solid crust form and fail. Form and fail, with the persistence of waves trying to hold their shape. These protocrustal patches rarely survive more than a few 100,000 years before being pulled back into the convecting mantle, recycled like autumn leaves returned to soil. Yet each failure teaches the planet something about the architecture of permanence. Each dissolved attempt at solid ground adds its chemical signature to the growing reservoir of materials that will eventually construct the first lasting landmasses. In these early millennia, the mystery of crustal stability remains one of geology's most profound puzzles. Scientists still debate exactly when and how the first permanent landmasses achieved enough buoyancy and structural integrity to resist being recycled back into the mantle's embrace. Some evidence, preserved in the oldest zircon crystals found in Western Australia, suggests that thin rafts of solidified rock floated briefly on the magma ocean's surface like ice flows on a planetary sea, only to be pulled under by inexorable convection currents and dissolved into the greater molten mass. These ancient crystals, no larger than grains of sand, represent some of the only surviving witnesses to Earth's earliest attempts at creating lasting geography. Other researchers propose that the first stable crust formed around the circular scars of impact craters, where massive asteroid and comet strikes temporarily cooled and thickened the planetary skin. The energy of these collisions, paradoxically, may have created the first islands of relative stability in an otherwise fluid world. Impact melts, counterintuitively, sometimes cool more slowly than the surrounding magma ocean, allowing for the formation of thicker, more buoyant crustal material that could resist subduction for slightly longer periods. The bombardment from space continues its relentless percussion, the late heavy bombardment delivering impacts that dwarf anything in recorded history. Each collision briefly melts whatever crust has managed to solidify, turning nascent continents back into temporary lakes of molten rock. Yet with each impact, the planet grows incrementally larger, its gravitational pull incrementally stronger, and the raw materials for continental formation accumulate like sediment in the depths of geological time. The largest impactors deliver not just destructive energy, but also exotic minerals and volatile compounds that will become essential components of future continental crust. The irony settles like volcanic ash across this primordial landscape. This most restless period in Earth's history will eventually give birth to the most stable geological features on the planet's surface. Ancient continental cores, once properly formed and established, will persist for billions of years, outlasting entire evolutionary lineages, ice ages, and the rise and fall of mountain ranges that will seem permanent by human standards but represent mere moments in deep time. These future continental shields will become the stable platforms upon which complex life will eventually flourish. Yet their origins lie in this epoch of seemingly endless instability. The planet practices impermanence with the dedication of a meditation master, and the surface remains a philosophical exercise in the temporary nature of all apparently solid things. Rock behaves more like thick honey, flowing and pooling according to temperature gradients and pressure differentials that shift with the planet's internal tides. What appears solid to any hypothetical observer would reveal itself as merely slow-moving liquid when viewed across the appropriate timescales. Beneath the roiling surface, the first chemical signatures of future granitic rocks begin their patient assembly. The processes of partial melting and fractional crystallization work their subtle alchemy, gradually concentrating the lighter elements silicon, aluminum, potassium, sodium that will become the fundamental building blocks of continental crust. These elements rise through the denser basaltic material like oil through water, accumulating in small pockets and lenses that represent the embryonic stages of what will become vast continental masses. The magnetic field, still weak and irregular, offers little protection from solar radiation, allowing charged particles to strip away atmospheric components and further heat the surface through electromagnetic interactions. This cosmic vulnerability adds another layer of instability to an already chaotic system, yet it also drives chemical reactions that will prove essential for the formation of the first stable crustal minerals. Only took 4.5 billion years to figure out how to make rocks that last longer than a geological season. Only required the patience of planetary-scale trial and error, the gradual accumulation of failed experiments in permanence, the slow education of a young world learning the fundamental principles of its own construction. The eventual success of continental formation will seem inevitable in hindsight. But here, in these foundational moments, nothing is certain except change, and even change itself remains subject to change. The first stone islands rise from Earth's molten sea like the memory of something solid trying to remember itself into existence. These are not the dramatic volcanic peaks that later epochs will celebrate, but humble, temporary protrusions barely more substantial than foam on the surface of a cosmic ocean. They emerge where the planet's internal convection currents happen to concentrate slightly cooler material, where the dance of heat and chemistry creates momentary refugees from the surrounding inferno. Each protocontinent begins as nothing more than a thickening in the global magma ocean, a place where partially crystallized minerals accumulate like sediment in a slow-moving river. The process unfolds with the patience that only geological time can afford. Plagioclase feldspar crystals, lighter than the surrounding basaltic melt, float upward through the molten rock like bubbles rising through syrup. Pyroxene and olivine, denser and more refractory, sink back toward the depths, leaving behind increasingly silica-rich compositions that will form the chemical foundation of future continental crust. The first of these embryonic landmasses measures perhaps a few hundred kilometers across, no larger than a modest island nation. Yet representing a revolutionary development in planetary architecture, its surface rises barely a few hundred meters above the surrounding magma ocean, an elevation so modest that it would be invisible from space, lost in the heat shimmer and volcanic haze that shrouds the early Earth. Yet, this humble prominence represents the planet's first successful experiment in creating something approaching permanent geography. The temperature differential between these slightly elevated regions and the surrounding molten landscape creates the planet's first weather systems of sorts, not the familiar patterns of wind and precipitation that will characterize later climate, but convective cells of superheated gas that circulate according to the subtle topography of the cooling surface. Sulfur dioxide and water vapor rise from the hotter regions, condense slightly as they encounter the marginally cooler air above the protocontinents, then descend again in patterns that foreshadow the atmospheric circulation systems of more temperate futures. Scientists studying the isotopic signatures preserved in the oldest surviving rocks find evidence of these ancient processes encoded in the crystal lattices of minerals that formed during this primordial period. The ratios of oxygen isotopes, the trace concentrations of rare earth elements, the subtle variations in radiogenic isotope systems all preserve a chemical memory of conditions so extreme that they challenge our understanding of how solid rock can form and persist under such hostile circumstances. The mystery of buoyancy governs these early experiments in continental formation. Why do some regions of partially molten crust remain at the surface, while others are pulled back into the mantle's embrace? The answer involves a delicate balance of density, temperature, and chemical composition that geologists are still working to understand fully. The successful protocontinents appear to achieve a critical threshold of differentiation, accumulating enough low-density minerals to resist the gravitational pull that recycles most early crustal material back into the planet's interior. The irony of these first landmasses lies in their simultaneous fragility and historical importance. They persist for mere millions of years, an eye blink in geological terms, yet they establish the fundamental patterns that will govern continental formation for the rest of Earth's history. Each temporary island represents a successful experiment in the physics of crustal buoyancy, a proof of concept for the more substantial continents that will follow. Their brief existence teaches the planet the basic principles of making rock that floats. Around the margins of these primitive land masses, the first crude approximations of shorelines begin to take shape. The boundary between solid and liquid remains indistinct, a gradual transition zone where partially crystallized mush gives way to fully molten rock. These are not the sharp coastal boundaries that will characterize later geological periods, but broad zones of intermediate consistency, neither fully solid nor completely liquid, but something in between that has no equivalent in the modern world. The chemical evolution of these early crustal fragments proceeds through processes that will become fundamental to all future continental formation. Fractional crystallization separates minerals according to their melting points and densities, creating increasingly evolved compositions as successive generations of crystals form and either accumulate or sink back into the melt. Partial melting of previously formed crustal material begins the recycling processes that will eventually produce the granitic compositions characteristic of mature continental crust. Heat flow from the planet's interior remains intense enough to maintain these protocontinents in a state of semi-solid plasticity. They deform continuously under their own weight and the stresses imposed by the surrounding convecting mantle, flowing like extremely viscous putty while maintaining just enough structural integrity to remain at the surface. This constant deformation prevents the formation of rigid geological structures, but allows the development of primitive layering and compositional gradients that will influence later crustal evolution. The atmosphere above these first islands consists primarily of water vapor, carbon dioxide, nitrogen, and various sulfur compounds outgassed from the extensive volcanic activity. The greenhouse effect maintains surface temperatures well above the boiling point of water at standard pressure, creating conditions where any water that manages to condense immediately returns to vapor. Yet even under these extreme conditions, the slightly elevated topography of the proto-continents creates subtle variations in atmospheric pressure and temperature that represent the earliest forms of continental climate differentiation. Only took a few 100 million years to discover that making temporary islands was easier than making permanent ones. Only required the planet to experiment with thousands of failed proto-continents before stumbling upon the chemical and physical principles that would eventually produce lasting landmasses. The eventual development of stable continental crust will build directly upon the lessons learned during this era of geological trial and error. But for now, these modest stone islands represent the cutting edge of planetary sophistication. The magnetic signatures preserved in the oldest crustal remnants suggest that even these temporary landmasses developed primitive magnetic field orientations, recording the chaotic behavior of Earth's early magnetic field as it struggled to establish stable patterns. These paleomagnetic records provide some of the only direct evidence for the existence and behavior of the planet's first attempts at creating lasting geography. Granite dreams in molten nights, and the planet begins its slow education in the chemistry of permanence. Deep beneath the temporary islands and the restless magma ocean, a more subtle transformation unfolds, the patient assembly of the rock type that will become the backbone of every future continent. This is not the dramatic volcanism that characterizes the surface, but a quieter process of molecular reorganization where silicon and aluminum atoms learn to arrange themselves into the crystalline architectures that will define continental crust for the remainder of Earth's history. The formation of granitic compositions requires a sophisticated dance of temperature, pressure, and chemical gradients that the young planet is only beginning to master. Unlike the straightforward basaltic magmas that dominate the surface formed through the relatively simple partial melting of the mantle, granite demands a more complex sequence of processes. Existing crustal material must be remelted, partially crystallized, and chemically fractionated through multiple cycles before achieving the distinctive composition that makes continental crust both lighter and more durable than its oceanic counterparts. In the deepest portions of the thickening crustal sections, temperatures reach the precise range where solid rock begins to behave like an extremely viscous liquid without losing its essential chemical identity. This zone of partial melting, hovering at temperatures between 7 and 900 degrees Celsius, becomes a natural laboratory for continental formation. Here, the more easily melted components of existing crustal rocks, quartz, alkali feldspar, and plagioclase begin to separate from the more refractory minerals, creating pockets of increasingly evolved magma that will eventually crystallize as granite. The process unfolds with the patience that characterizes all fundamental geological transformations. Over hundreds of thousands of years, these zones of partial melting develop complex internal structures. Melt-rich regions accumulate in structural low points, forming primitive magma chambers that serve as staging areas for the chemical evolution toward granitic compositions. The surrounding solid framework continues to provide structural support while allowing the gradual migration and concentration of the lighter, more silica-rich melts. Scientists studying the oldest preserved granitic rocks find evidence of this ancient apprenticeship in continental formation encoded in their mineral textures and chemical signatures. The trace element patterns reveal multiple episodes of melting and crystallization, each cycle further refining the chemical composition toward the idealized granite that will become synonymous with stable continental crust. These ancient rocks preserve a record of the planet's gradual mastery of the complex physical and chemical processes required to build lasting landmasses. The mystery of granite formation during this early period centers on the question of water content in the primitive crustal melts. Modern granite formation depends heavily on the presence of dissolved water, which dramatically lowers melting temperatures and promotes the chemical differentiation processes that create granitic compositions. Yet, the early Earth's surface conditions with temperatures well above the boiling point of water make it unclear how sufficient water could remain dissolved in crustal melts long enough to facilitate granite formation. Some researchers propose that water was sequestered in the crystal structures of hydrous minerals deep within the thickening crustal sections, where pressure could maintain water in solution despite the extreme surface temperatures. Others suggest that the early granites formed through anhydrous processes that have no direct equivalent in modern geological environments, representing a style of crustal evolution that became extinct as the planet cooled and water became more readily available at shallow crustal levels. The irony of these early granitic formations lies in their simultaneous sophistication and fragility. The chemical processes required to create granite represent some of the most complex transformations in all of geochemistry, involving the precise coordination of temperature, pressure, and fluid chemistry that rivals the complexity of biological systems. Yet these early granites form in crustal sections that remain vulnerable to recycling back into the mantle, making their sophisticated chemistry temporary and their existence precarious. The first successful accumulations of granitic material begin to exhibit the fundamental property that will make continental crust possible. Density contrast with the underlying mantle. Granite's relatively low density, approximately 2.7 grams per cubic centimeter compared to the mantle's 3.3, creates the buoyancy necessary for long-term crustal stability. These early granitic bodies begin to behave like geological corks, rising through the denser surrounding material and accumulating near the surface where they can contribute to the formation of more permanent land masses. The textural evidence preserved in ancient granitic rocks reveals the slow, incremental nature of their formation. Large crystals of feldspar and quartz show complex zoning patterns that record changing chemical conditions during crystallization, multiple generations of mineral growth. Separated by episodes of partial remelting and chemical modification, create microscopic landscapes that tell the story of the planet's gradual learning process in continental construction. Heat production from the decay of radioactive elements uranium, thorium, and potassium. Concentrated in these evolving granitic compositions begins to create internal heat sources that will eventually become characteristic of continental crust. This radiogenic heating establishes a positive feedback loop. The formation of granite concentrates heat-producing elements, which maintain elevated temperatures that promote further granite formation, gradually building the thermal structure that will characterize mature continental crust. The magnetic properties of these early granitic rocks provide additional clues about the conditions under which they formed. The presence of magnetite and other iron-bearing minerals records the oxygen fugacity of the crystallizing magmas, offering insights into the atmospheric and crustal conditions that prevailed during this critical period of continental evolution. These paleomagnetic signatures suggest that even the earliest granites formed under chemical conditions that were beginning to diverge from the highly reducing environment that characterized the planet's initial formation. Around the margins of the developing granitic bodies, hybrid rocks begin to form where the evolved magmas interact with the surrounding basaltic material. These transitional compositions, neither fully granitic nor purely basaltic, represent the planet's first experiments in creating the complex mineralogical diversity that will characterize mature continental crust. The formation of these intermediate rock types demonstrates the beginning of the chemical stratification that will eventually make continental crust fundamentally different from oceanic crust. Only took several hundred million years to figure out that making granite required more than just melting rocks. It demanded the patient cultivation of the right chemical conditions over geological timescales. Only required the planet to develop an intuitive understanding of the complex thermodynamics that govern silicate melt evolution. The eventual mastery of granite formation will make possible the construction of continental masses large enough to influence global climate and ocean circulation. But for now, these early experiments represent the first tentative steps toward geological sophistication. The volatile elements dissolved in these early granitic melts, water, carbon dioxide, sulfur compounds begin to establish the complex fluid chemistry that will become essential to all future crustal processes. These primitive volcanic emanations represent the planet's first attempts at developing the hydrothermal systems that will eventually support the chemical environments necessary for life. The slow gathering begins across the planet's restless surface, as scattered fragments of proto-continental crust discover the inexorable attraction that will define their geological destiny. These are not dramatic collisions that shake the heavens, but patient convergences that unfold over tens of millions of years, crustal patches drifting toward each other with the persistence of continents learning to become continental. The forces driving this assembly operate on scales so vast and timescales so extended that they dwarf human comprehension, yet their effects will shape every aspect of Earth's future geography. The mechanism of this early crustal accretion remains one of the most elegant examples of planetary self-organization. As the scattered granitic bodies achieve sufficient size and buoyancy to resist recycling into the mantle, they begin to influence the convection patterns in the underlying molten rock. Each stable crustal fragment creates a thermal blanket effect, insulating the mantle material beneath and causing it to heat up relative to surrounding regions. This differential heating drives convective cells that gradually transport the overlying crustal material towards zones of convergence, like leaves being swept together by gentle currents in a vast, molten pond. The process exhibits a fundamental asymmetry that will characterize continental formation throughout Earth's history. Smaller crustal fragments move more readily than larger ones, creating a natural hierarchy where the most mobile pieces are preferentially accreted onto the margins of more stable, stationary masses. This size-dependent mobility ensures that continental growth proceeds through the systematic capture of progressively smaller fragments, building continental masses through a process that resembles geological crystallization more than mechanical collision. The first successful crustal collisions occur where two roughly equal-sized granitic bodies approach each other across narrowing expanses of molten rock. The convergence unfolds with agonizing slowness, perhaps a few centimeters per year at most, allowing both crustal fragments to undergo extensive internal deformation as they respond to the gradually increasing stresses. The boundaries between the converging masses develop complex zones of partial melting and recrystallization, creating hybrid rock types that preserve a detailed record of the accretion process. Scientists studying the structural geology of the oldest continental fragments find evidence of these ancient collisions preserved in the orientations of mineral grains and the patterns of rock deformation. Microscopic analysis reveals that many apparently uniform granitic bodies actually consist of multiple smaller fragments that were welded together during these early accretion events. The boundaries between original crustal pieces can be traced through subtle variations in chemical composition and mineral texture, creating geological maps of processes that occurred billions of years ago. The mystery of crustal welding during this early period involves understanding how separate fragments of solid rock can become permanently joined without losing their individual chemical identities. Modern plate tectonic processes provide clear mechanisms for continental collision and suturing. But the conditions on early Earth, with surface temperatures well above the melting point of many rock types, created environments where the boundary between collision and assimilation became unclear. Current research suggests that the welding process involved the formation of zones of granitic magma along the convergent boundaries, where the heat generated by mechanical deformation and the insulating effect of the thickening crust combined to create temperatures sufficient for partial melting. These magmatic suture zones acted as geological glue, bonding the separate crustal fragments into larger, more coherent masses while preserving evidence of their originally separate identities. The irony of these early accretion events lies in their combination of geological violence and structural delicacy. The forces required to move and deform crustal fragments operate on scales that dwarf any modern geological process. Yet the resulting structures often preserve microscopic details of the original rock textures and mineral compositions. This preservation of fine-scale features within large-scale deformational events demonstrates the planet's growing sophistication in managing the complex mechanical and thermal processes involved in continental construction. The timing of crustal convergence appears to be controlled by the cooling history of the planet's interior. As the overall heat flow from the mantle gradually decreases, the zones of partial melting that facilitate crustal mobility become more restricted and less efficient. This thermal evolution creates a narrow window of opportunity for large-scale crustal accretion too early, and the crust remains too hot and mobile to maintain structural integrity too late, and the driving forces become insufficient to overcome the mechanical strength of the cooling crustal fragments. The chemical consequences of crustal accretion extend far beyond the simple addition of material to growing continental masses. The collision and welding of separate granitic bodies creates opportunities for large-scale chemical mixing and differentiation that would be impossible within individual crustal fragments. The formation of suture zones provides pathways for fluid migration and chemical exchange between previously isolated crustal domains, leading to the development of increasingly complex and chemically evolved rock types. The gravitational effects of the growing continental masses begin to influence the behavior of the surrounding magma ocean. Larger crustal fragments create significant gravitational anomalies that deflect convection patterns and influence the trajectories of smaller crustal pieces. This gravitational focusing effect accelerates the accretion process, creating a positive feedback loop where larger continental masses attract additional material at increasing rates. The development of primitive mountain ranges begins during this phase of crustal accretion, where converging crustal fragments have different mechanical properties or chemical compositions. The collision process creates zones of preferential deformation and uplift. These early mountain systems lack the dramatic topographic relief that will characterize later orogenic events, but they represent the planet's first experiments in creating significant vertical relief on its surface. The magnetic signatures preserved in accreted crustal fragments provide crucial evidence for understanding the kinematics of early continental assembly. Paleomagnetic analysis reveals that many crustal pieces underwent significant rotation during the accretion process, indicating that the collisions involved complex three-dimensional motions rather than simple head-on encounters. These rotational components suggest that the early accretion events were influenced by the Coriolis effects associated with planetary rotation, establishing patterns that will continue to influence continental tectonics throughout Earth's history. The volatile elements released during crustal accretion begin to create the first significant chemical modifications of the primitive atmosphere. The heat generated by collision and deformation drives off water vapor, carbon dioxide, and other gases that had been dissolved in the crustal rocks, contributing to atmospheric evolution and potentially influencing the planet's overall thermal balance. These early degassing events represent the beginning of the complex interactions between solid Earth processes and atmospheric chemistry that will become increasingly important as the planet continues to evolve. Only took a few 100 million years to discover that building continents required more than just making continental crust. It demanded the development of sophisticated mechanisms for moving and joining separate crustal fragments. Only required the planet to invent the basic principles of plate tectonics through trial and error, learning to orchestrate the movement of solid rock across its surface. The eventual mastery of continental accretion will make possible the formation of supercontinents large enough to influence global climate patterns. But for now, these early gathering events represent the first tentative steps toward large-scale geological organization. When mountains were born sideways, the planet discovered that building upward required first learning to push inward with the patience of geological compression. These are not the towering peaks that will one day scratch the sky, but the first hesitant experiments in vertical relief, modest swells and ridges that rise barely a few hundred meters above the surrounding crustal plains, yet represent a revolutionary development in Earth's architectural capabilities. The process unfolds through horizontal forces so vast and persistent that they gradually convince solid rock to abandon its preference for lying flat and instead reach tentatively toward the primitive atmosphere. The fundamental mechanics of mountain building during this early period operate on principles that will remain unchanged throughout Earth's history. Yet the specific conditions create unique challenges for crustal deformation. The high surface temperatures maintain the continental crust in a state of elevated ductility, allowing large-scale folding and flow rather than the brittle fracturing that characterizes mountain building in cooler geological periods. Entire crustal sections behave more like warm honey than solid rock, deforming continuously under stress while maintaining their basic structural integrity. The first successful mountain building events occur where converging crustal fragments develop sufficient mechanical contrast to focus deformation into narrow zones. These proto-orogenic belts form along the suture zones where separate granitic bodies have been welded together, creating linear weaknesses in the crustal structure that preferentially accommodate the horizontal shortening imposed by continuing convergence. The resulting deformation creates broad, gentle folds with wavelengths measured in tens of kilometers and amplitudes of only a few hundred meters, geological wrinkles that barely qualify as topographic relief by modern standards. The chemical processes accompanying early mountain formation involve the mobilization and redistribution of volatile elements on scales that dwarf modern hydrothermal systems. The combination of elevated temperatures, mechanical stress, and fluid flow creates conditions where water, carbon dioxide, and sulfur compounds can migrate freely through the deforming crustal rocks, promoting chemical reactions and mineral transformations that would be impossible under less extreme conditions. These early metamorphic processes represent the planet's first experiments in the high-pressure, high-temperature mineral chemistry that will become characteristic of deep crustal environments. Scientists studying the structural geology of ancient mountain remnants find evidence of these primitive orogenic processes preserved in the orientations and distributions of mineral grains within deformed rocks. Microscopic analysis reveals complex patterns of crystal plasticity and recrystallization that record the stress fields and thermal conditions prevalent during early mountain building. The presence of high-temperature mineral assemblages and the systematic orientation of deformed crystals provide detailed reconstructions of the forces and processes that shaped these ancient landscapes. The mystery of topographic relief during this early period centers on the question of erosional processes and their effectiveness under the extreme surface conditions. With atmospheric temperatures well above the boiling point of water, conventional weathering and erosion mechanisms would have been largely inoperative. Yet some process must have been removing material from the emerging highlands to prevent them from growing to unrealistic elevations. Current models suggest that thermal expansion and contraction, combined with chemical corrosion by the dense, reactive atmosphere, provided primitive erosional mechanisms that could limit topographic growth. Alternative hypotheses propose that the high atmospheric pressures and temperatures actually enhanced certain erosional processes, creating conditions where rock surfaces could be chemically dissolved or mechanically abraded at rates that exceeded those found in modern environments. The dense, sulfur-rich atmosphere may have acted as a corrosive agent capable of attacking even resistant granitic compositions, creating a balance between uplift and erosion that maintained modest topographic relief despite the intense compressive forces driving mountain formation. The irony of these early mountain-building episodes lies in their simultaneous geometric simplicity and mechanical complexity. The resulting topographic forms, broad, gentle undulations with simple, predictable geometries, appear deceptively straightforward. Yet the physical processes required to create even modest relief under such extreme conditions involved sophisticated interactions between thermal, mechanical, and chemical factors that challenge our understanding of crustal behavior. The gravitational effects of emerging topographic relief begin to influence atmospheric circulation patterns in ways that foreshadow the complex climate interactions that will characterize later geological periods. Even modest elevation differences create pressure gradients and temperature variations that drive primitive convection cells in the dense atmosphere. These early atmospheric circulation patterns represent the planet's first experiments in topographically controlled weather systems, establishing feedback loops between solid Earth processes and atmospheric dynamics. The thermal consequences of crustal thickening during mountain building create the first significant variations in heat flow across the planet's surface. Thicker crustal sections provide more effective insulation for the underlying mantle, leading to increased temperatures at depth and enhanced rates of radiogenic heat production. This thermal blanketing effect establishes temperature gradients that will persist for hundreds of millions of years, influencing subsequent magmatic processes and crustal evolution long after the original mountain-building forces have ceased. The development of structural fabric within the deforming crustal rocks creates the first systematic patterns of mechanical anisotropy in continental crust. The preferential alignment of mineral grains and the formation of foliation planes establish directions of weakness and strength that will influence all subsequent deformation events. These structural inheritances represent a form of geological memory, where the mechanical effects of early mountain building are preserved and influence the response of the crust to later tectonic stresses. The fluid flow systems associated with early orogenic processes begin to establish the complex hydrothermal networks that will become essential to many future geological processes. The combination of elevated temperatures, mechanical fracturing, and chemical gradients drives large-scale fluid circulation patterns that transport dissolved minerals and redistribute chemical components throughout the thickening crustal sections. These primitive hydrothermal systems represent the planet's first experiments in fluid-mediated chemical transport and mineral precipitation. The magnetic properties of rocks formed during early mountain building preserve detailed records of the stress orientations and thermal conditions that prevailed during deformation. Paleomagnetic analysis reveals that many orogenic belts underwent significant tilting and rotation during the mountain building process, providing kinematic constraints on the three-dimensional nature of early crustal deformation. These magnetic records represent some of the most direct evidence available for understanding the mechanics of primitive orogenic processes. The seismic properties of early mountain systems suggest that they were characterized by much higher levels of internal deformation and mechanical instability than modern mountain ranges. The elevated temperatures and ductile behavior of the crustal rocks promoted continuous adjustment and flow, rather than the episodic brittle failure that generates earthquakes in cooler crustal environments. This difference in mechanical behavior created mountain systems that were inherently more stable in the short term, but more susceptible to long-term modification by erosion and thermal processes. Only took several tens of millions of years to figure out that making mountains required more than just pushing rocks together. It demanded the careful orchestration of thermal, mechanical, and chemical processes across vast scales of space and time. Only required the planet to develop an understanding of the complex feedback relationships between topographic relief, atmospheric circulation, and crustal thermal structure. The eventual mastery of mountain building will create topographic barriers capable of influencing global weather patterns and oceanic circulation. But for now, these modest ridges represent the cutting edge of planetary sophistication in vertical construction. The great cooling breath begins its patient work across the planet's molten surface, and Earth slowly learns the art of making temperatures that allow permanence. This is not the dramatic thermal collapse that some planetary models predict, but a gradual, almost imperceptible decrease in surface heat that unfolds over hundreds of millions of years, a planetary exhale so gentle that it spans geological epochs, yet so fundamental that it will determine the possibility of every future geological process. The cooling follows no simple exponential curve, but exhibits the complex rhythm of a world, learning to balance the competing demands of internal heat production and radiative heat loss. The mechanism of planetary cooling operates through the intricate interplay between atmospheric greenhouse effects, volcanic outgassing, and the gradual decline in radiogenic heat production as short-lived isotopes decay. The dense carbon dioxide atmosphere that blankets the early Earth creates a greenhouse effect so intense that surface temperatures remain above 400 degrees Celsius for hundreds of millions of years after the planet's initial formation. Yet even this extreme greenhouse warming cannot entirely compensate for the steady decrease in internal heat generation as the planet's radioactive inventory gradually depletes. The first signs of meaningful cooling appear in the behavior of volcanic systems, where magma compositions begin to shift toward more silica-rich types that require lower temperatures to remain molten. The gradual evolution from purely basaltic volcanism toward more intermediate and eventually granitic compositions reflects the planet's growing ability to sustain lower temperature melting processes. This compositional evolution represents one of the most sensitive indicators of decreasing planetary temperatures, recording thermal changes too subtle to measure directly, but profound enough to alter fundamental geochemical processes. The development of stable surface temperatures proceeds through a series of thermal plateaus and gradual transitions that reflect the complex feedback relationships between atmospheric composition, volcanic activity, and crustal thermal structure. Each decrease in average surface temperature creates conditions that favor the preservation of more highly evolved crustal compositions, which in turn influence the chemistry of volcanic gases and atmospheric greenhouse warming. These feedback loops create a self-regulating system that moderates the rate of cooling and prevents the dramatic thermal transitions that could destabilize early crustal formation. Scientists studying the thermal evolution of the early Earth rely primarily on indirect evidence preserved in the chemical compositions and crystal structures of ancient minerals. The titanium in zircon thermometer, calibrated through laboratory experiments on synthetic zircon crystals, provides estimates of crystallization temperatures for some of the oldest surviving crustal materials. These measurements suggest that surface temperatures dropped below 300 degrees Celsius sometime between 4 and 3.5 billion years ago, marking the beginning of conditions that could support more stable continental crust formation. The mystery of atmospheric water vapor during this cooling period remains one of the most challenging aspects of early Earth thermal evolution. The gradual decrease in surface temperatures should have promoted the condensation of water vapor from the atmosphere, yet the geological record provides ambiguous evidence for the timing and extent of early ocean formation. Some researchers propose that water remained in the vapor phase until surface temperatures dropped below the critical point for water, while others suggest that high atmospheric pressures could have maintained liquid water even at elevated temperatures. Isotopic evidence from ancient sedimentary rocks suggests that liquid water existed on Earth's surface much earlier than simple thermal models would predict, implying that local cooling and condensation occurred in isolated regions, even while global average temperatures remained above the boiling point. These early aqueous environments may have been restricted to polar regions, high elevation areas, or zones where atmospheric circulation created localized pressure and temperature conditions favorable for water condensation. The irony of planetary cooling lies in its simultaneous necessity and threat to early crustal development. Lower temperatures enable the formation of more stable continental crust and create conditions favorable for complex geochemical processes. Yet the same cooling that promotes crustal stability also reduces the efficiency of the convective systems that drive crustal accretion and mountain building. This thermal paradox creates a narrow window of optimal conditions for continental formation, requiring a delicate balance between sufficient heat to maintain crustal mobility and sufficient cooling to enable long-term stability. The thermal evolution of the planet's interior proceeds independently of surface cooling, following the much slower timescales associated with radiogenic decay and secular cooling of the deep mantle. The temperature difference between the hot interior and the cooling surface creates increasingly steep thermal gradients that enhance convective heat transport and influence the dynamics of crustal formation. These evolving thermal gradients establish the fundamental architecture of planetary heat flow that will persist throughout Earth's subsequent history. The chemical consequences of atmospheric cooling extend far beyond simple temperature effects to influence the fundamental chemistry of surface and near-surface environments. The gradual condensation of water vapor creates opportunities for aqueous geochemical processes that were impossible under the extreme conditions of the early atmosphere. The formation of primitive hydrological cycles begins to establish chemical weathering processes that will become essential to long-term planetary evolution. The development of thermal stratification within the cooling atmosphere creates the first systematic variations in atmospheric chemistry with altitude. The denser, hotter air near the surface maintains higher concentrations of reactive gases and volcanic emanations, while the cooler upper atmosphere begins to develop distinct chemical characteristics. This atmospheric layering establishes the foundation for complex atmospheric chemistry and creates environments where different types of chemical reactions can occur simultaneously at different elevations. The magnetic field intensity appears to respond to changes in core thermal structure associated with planetary cooling, though the relationships remain poorly understood. Paleomagnetic evidence suggests that the early magnetic field was both stronger and more variable than modern field conditions, possibly reflecting the vigorous convection in the liquid core driven by rapid cooling and crystallization of the inner core. These magnetic variations create additional complexities in interpreting the paleomagnetic records that provide our primary evidence for early crustal behavior. The solidification of the first permanent ice begins in isolated regions where local atmospheric conditions create temperatures below the freezing point of water. These early ice formations represent the planet's first experiments with solid water, establishing chemical and physical processes that will become fundamental to future climate systems. The presence of ice creates new mechanisms for chemical weathering and erosion that begin to compete with the high-temperature processes that dominated earlier surface evolution. The thermal relaxation of stressed crustal rocks creates the first systematic patterns of fracturing and joint development that will become characteristic of cooling continental crust. The differential thermal contraction of rocks, with different mineral compositions and thermal expansion coefficients, creates stress patterns that promote the formation of systematic fracture networks. These cooling-related structures provide pathways for fluid flow and chemical transport that enhance weathering processes and promote further crustal evolution. The establishment of more moderate thermal conditions creates environments where complex organic chemistry becomes theoretically possible for the first time in Earth's history. While life itself remains hundreds of millions of years in the future, the cooling planet begins to develop temperature regimes where organic molecules could potentially remain stable for extended periods. This thermal transition represents a fundamental prerequisite for all subsequent biological evolution. Only took several hundred million years to figure out that making a habitable planet required more than just cooling down. It demanded the careful orchestration of atmospheric, oceanic, and crustal thermal systems across multiple timescales. Only required the planet to develop sophisticated feedback mechanisms that could maintain thermal stability while allowing continued geological evolution. The eventual achievement of moderate surface temperatures will make possible the development of complex hydrological and biological systems. But for now, this great cooling breath represents the first tentative step toward a more temperate future. Rivers that carved nothing flow across the barren landscape of early Earth, carrying their liquid burden over surfaces that have never known the gentle persistence of erosion. These are not the familiar waterways that will one day sculpt valleys and transport sediments from mountains to seas, but primitive streams of superheated water that exist in the narrow margin between liquid and vapor, flowing across rock surfaces so hot that they glow with dull red heat. The water moves with the determination of gravity, yet leaves no permanent mark upon the stone, evaporating and condensing in endless cycles that accomplish nothing more than the redistribution of heat across the planetary surface. The first successful rivers emerge where local atmospheric conditions create temperatures cool enough for water to remain stable in liquid form for more than a few minutes at a time. These early waterways follow the subtle topographic gradients created by uneven cooling of the crustal surface, seeking the lowest elevations with the same persistence that will characterize all future river systems. Yet their channels remain temporary, existing only as long as the specific thermal conditions that created them persist, disappearing when atmospheric circulation shifts or local volcanic activity raises surface temperatures above the stability threshold for liquid water. The chemistry of these primitive rivers differs fundamentally from any aqueous system that will exist in later geological periods. The water carries dissolved loads of sulfur compounds, carbon dioxide, and volcanic gases that create solutions so corrosive they can dissolve even the most resistant rock types. The pH values approach levels that would be considered extreme by modern standards, creating chemical environments where normal weathering processes cannot operate and where the boundary between solution and precipitation remains in constant flux. The thermal properties of early river water create flow dynamics that have no equivalent in modern hydrological systems. The elevated temperatures reduce water density and viscosity while increasing vapor pressure, creating streams that behave more like flowing gas than liquid water. The constant evaporation and condensation along the flow path creates complex circulation patterns where water moves both horizontally along the surface and vertically through repeated phase transitions. Scientists studying the geochemical signatures preserved in ancient sedimentary rocks find evidence of these early aqueous systems encoded in the isotopic compositions and trace element patterns of minerals that formed during this period. The oxygen isotope ratios in ancient cherts and other chemical sediments suggest crystallization from waters at temperatures well above 100 degrees Celsius, confirming the existence of liquid water systems under extreme thermal conditions that would be impossible to maintain under modern atmospheric conditions. The mystery of channel formation during this early period involves understanding how flowing water could create persistent topographic features when the substrate remained at temperatures high enough to promote rapid thermal expansion and chemical alteration. Modern river channels depend on the mechanical erosion of relatively cool, stable rock surfaces. But early Earth conditions created environments where thermal and chemical erosion processes operated at rates that could eliminate channels as quickly as flowing water could carve them. Current research suggests that the first persistent river channels formed where flowing water encountered zones of crustal weakness created by structural deformation or compositional variations. These pre-existing linear features provided pathways that could focus water flow and create sufficient thermal contrast to enable local cooling and channel stabilization. The resulting waterways represented a collaboration between hydrological and geological processes, where water flow and crustal structure worked together to create the first stable aqueous transport systems. The irony of these early river systems lies in their combination of hydrological sophistication and geomorphological impermanence. The physics of water flow operates according to the same fundamental principles that will govern all future river systems, creating complex patterns of velocity distribution, sediment transport capacity, and hydraulic energy that rival modern waterways in their complexity. Yet the extreme thermal conditions prevent these sophisticated flow systems from leaving any lasting record of their existence in the landscape. The evaporation rates along early river courses create the first systematic patterns of atmospheric humidity variation across the planetary surface. The intense evaporation from flowing water establishes localized regions of elevated water vapor concentration that influence atmospheric circulation patterns and create primitive weather systems. These early hydrological contributions to atmospheric dynamics represent the beginning of the complex interactions between surface water and atmospheric processes that will become fundamental to Earth's climate system. The chemical transport capacity of high-temperature river water enables the mobilization and redistribution of dissolved minerals on scales that dwarf modern aqueous geochemical systems. The elevated solubility of most rock-forming minerals under extreme temperature and pH conditions allows single river systems to transport the chemical equivalent of entire mountain ranges, creating opportunities for large-scale geochemical differentiation and mineral concentration that will influence crustal evolution for hundreds of millions of years. The thermal effects of flowing water on the underlying rock surfaces create the first systematic patterns of thermally induced weathering and alteration. The rapid temperature cycling associated with water flow and evaporation generates thermal stresses that promote mechanical fracturing and chemical alteration of rock surfaces. These thermally driven weathering processes represent a fundamentally different style of surface modification than the conventional chemical and mechanical weathering that will characterize later geological periods. The development of primitive drainage networks begins during this phase of early hydrological evolution. The tendency for water to flow downhill creates branching patterns of temporary channels that follow the topographic gradients imposed by uneven crustal cooling and structural deformation. These early drainage systems exhibit the same geometric properties and scaling relationships that will characterize all future river networks, demonstrating that the fundamental organizing principles of surface water flow were established during the earliest phases of planetary evolution. The sediment transport capacity of high-temperature river water differs significantly from modern systems due to the altered physical properties of the water and the enhanced chemical reactivity of the transported materials. The reduced density and viscosity of hot water creates flow conditions that favor the transport of finer-grained materials, while the corrosive chemistry promotes the rapid dissolution of larger particles. These transport characteristics create distinctive patterns of sediment distribution that will influence the chemical evolution of early sedimentary systems. The interaction between flowing river water and the primitive atmosphere creates the first significant source of atmospheric water vapor that is not directly related to volcanic outgassing. The evaporation from river surfaces contributes to atmospheric humidity and influences the distribution of condensation nuclei that control cloud formation and precipitation patterns. These early contributions to the hydrological cycle represent the beginning of surface-atmosphere water exchange processes that will become increasingly important as planetary cooling continues. The magnetic properties of minerals precipitated from early river water preserve detailed records of the chemical and thermal conditions that characterize these ancient aqueous systems. Paleomagnetic analysis of chemical sediments formed in early river environments provides constraints on water temperatures, pH conditions, and dissolved chemical loads that complement the geochemical evidence for extreme early Earth surface conditions. The biological implications of early river systems remain largely theoretical, yet the existence of flowing liquid water creates environments where complex organic chemistry could theoretically operate for the first time in Earth's history. The chemical transport and concentration mechanisms associated with river flow establish processes that could potentially concentrate organic compounds and create chemical gradients that might favor the development of self-organizing chemical systems. Only took tens of millions of years to discover that making rivers required more than just having liquid water. It demanded the development of thermal conditions stable enough to maintain flowing water for geologically significant periods. Only required the planet to learn the complex thermodynamics of water-rock interaction under extreme conditions, developing the ability to maintain liquid water systems despite surface temperatures that remained well above modern boiling points. The eventual establishment of stable river systems will create the erosional and transport mechanisms necessary for complex sedimentary processes. But for now, these ephemeral waterways represent the first tentative experiments in surface hydrology. The dance floor expands as larger continental masses achieve sufficient size to influence global ocean currents and atmospheric patterns, marking the transition from isolated crustal experiments to integrated planetary systems. These growing landmasses no longer exist as passive passengers on the planet's molten surface, but begin to assert their presence through gravitational, thermal, and chemical effects that extend far beyond their physical boundaries. The continental fragments have reached a critical threshold where their existence starts to shape the very processes that created them, establishing feedback loops that will govern planetary evolution for the remainder of Earth's history. The mechanics of continental influence operate through the subtle but persistent modification of convection patterns in both the mantle and the primitive oceans. Larger continental masses create significant thermal anomalies that deflect the circulation of molten rock in the underlying mantle, channeling heat flow into preferred pathways and creating zones of enhanced or diminished volcanic activity. These thermal effects extend hundreds of kilometers beyond the continental margins, influencing the formation and destruction of oceanic crust in patterns that reflect the size and distribution of the overlying landmasses. The first clear evidence of continental influence on oceanic circulation appears in the chemical stratification of primitive seawater. The presence of large continental masses creates barriers to the free circulation of ocean currents, establishing distinct chemical provinces where different dissolved mineral loads and temperature regimes can develop. These early examples of oceanographic differentiation represent the planet's first experiments in creating regional environmental conditions, establishing the foundation for the complex biogeochemical cycling that will characterize later Earth systems. The atmospheric effects of growing continental masses manifest through the modification of pressure gradients and temperature distributions that drive primitive weather systems. Even modest topographic relief associated with continental margins creates sufficient perturbation of atmospheric flow patterns to generate localized circulation cells and pressure systems. The elevated temperatures maintained by continental thermal anomalies create convective updrafts that influence atmospheric mixing and the distribution of volcanic gases and water vapor. Scientists studying the paleoclimatic signatures preserved in ancient sedimentary sequences find evidence of these early continental climate effects recorded in the chemical compositions and depositional patterns of sedimentary rocks formed during this period. The isotopic signatures of oxygen and carbon in ancient carbonate minerals suggest the existence of distinct climatic provinces associated with continental versus oceanic regions, indicating that land masses had achieved sufficient size to create measurable environmental gradients. The mystery of continental climate influence during this early period centers on understanding how relatively small land masses could generate significant atmospheric and oceanic effects under the extreme conditions that characterized early Earth. Modern climate systems depend on large temperature contrasts between land and ocean surfaces to drive circulation patterns. Yet early Earth conditions maintained surface temperatures that were uniformly elevated across both continental and oceanic regions. Current research suggests that the climate influence of early continental masses operated primarily through elevation effects and thermal inertia differences, rather than the temperature contrasts that drive modern land-ocean climate interactions. The slightly elevated topography of continental regions created pressure gradients sufficient to influence atmospheric circulation, while the different thermal properties of continental versus oceanic crust created subtle but persistent variations in heat flow and surface temperature. The irony of early continental climate influence lies in the contrast between the modest physical size of these land masses and the profound effects they exerted on planetary scale processes. Continental fragments that covered less than 5% of Earth's surface could influence atmospheric and oceanic circulation patterns across the entire planet, demonstrating the non-linear nature of climate system responses and establishing principles that will continue to operate throughout subsequent geological periods. The gravitational effects of large continental masses begin to create systematic variations in sea level and oceanic depth that influence sedimentary processes and the distribution of volcanic activity. The isostatic depression of oceanic crust surrounding continental margins creates preferred sites for sediment accumulation and establishes drainage patterns that channel erosional products toward specific depositional environments. These gravitationally controlled topographic variations represent the beginning of systematic geographical differentiation of Earth's surface. The chemical evolution of continental masses during this phase involves the development of increasingly complex internal structure and compositional diversity. The thermal insulation provided by thick continental crust creates conditions favorable for extensive magmatic differentiation and the formation of highly evolved rock types. The development of internal chemical gradients within continental masses establishes the foundation for complex crustal architecture that will influence all subsequent geological processes. The magnetic signature of large continental masses creates the first systematic variations in planetary magnetic field strength and orientation across Earth's surface. The magnetic minerals concentrated in continental crust contribute to local magnetic anomalies that influence the behavior of charged particles in the early atmosphere and may have provided partial protection from solar radiation in continental regions. These magnetic effects represent an additional mechanism through which continental masses could influence surface environmental conditions. The development of primitive continental drainage systems begins to establish systematic patterns of chemical transport and redistribution that will become fundamental to global geochemical cycling. The erosional products of continental weathering create the first significant sources of terrigenous sediment, introducing new chemical components into oceanic systems and establishing the land-to-sea transport pathways that will become essential to many biogeochemical processes. The thermal evolution of large continental masses creates internal temperature gradients that drive complex hydrothermal circulation systems within the continental crust. These internal fluid flow networks transport dissolved minerals and redistribute chemical components on scales that influence the mechanical and chemical properties of entire continental blocks. The development of continental-scale hydrothermal systems represents a new level of geological organization that transcends the local-scale processes that characterized earlier crustal evolution. The seismic properties of large continental masses begin to exhibit the characteristic signatures that will distinguish continental from oceanic crust throughout subsequent geological history. The thick, chemically evolved continental crust develops distinctive seismic velocity structures and attenuation properties that reflect its complex internal architecture and thermal structure. These seismic characteristics provide the foundation for understanding continental structure and evolution through geophysical methods. The influence of continental masses on global volcanic activity creates the first systematic geographical variations in magmatic processes and volcanic gas emissions. The thermal blanketing effect of continental crust concentrates volcanic activity in preferred zones, while the chemical contamination of magmas by continental crustal material begins to create distinctive volcanic rock types. These continental influences on volcanism establish patterns of magmatic activity that will persist throughout Earth's subsequent evolution. The interaction between large continental masses and atmospheric circulation begins to create the first systematic patterns of atmospheric chemical transport and deposition. The deflection of atmospheric currents around continental topographic barriers establishes preferred pathways for the transport of volcanic gases and aerosols, creating regional variations in atmospheric chemistry and deposition rates that influence surface chemical weathering and mineral formation. The development of continental margins creates the first systematic transition zones between fundamentally different crustal types, establishing the geological and geophysical boundaries that will become fundamental to understanding Earth's surface structure. These early continental oceanic transitions exhibit many of the characteristics that will define such boundaries throughout subsequent geological history, demonstrating the fundamental nature of the processes that create and maintain continental margins. Only took several 100 million years to figure out that making continents required more than just assembling crustal fragments. It demanded the development of land masses large enough to influence planetary scale systems and create their own environmental conditions. Only required the planet to learn that continental formation and climate evolution represent coupled processes that must develop together through complex feedback relationships. The eventual achievement of continental masses large enough to influence global systems will make possible the development of complex environmental gradients and biogeochemical cycling. But for now, these expanding dance floors represent the first experiments in continental-scale environmental influence. Collision in geological time unfolds with the patient inevitability of gravity itself. As major continental blocks approach each other across shrinking ocean basins over hundreds of millions of years. This is not the dramatic impact that human imagination conjures, but a convergence so gradual that mountain ranges have time to rise and erode away during the approach phase alone. The process operates on timescales that dwarf the entire history of complex life, yet every stage leaves its signature in the rock record, creating a detailed archive of the planet's first experiments in large-scale tectonic organization. The mechanics of continental convergence during this early period operate through the systematic modification of mantle convection patterns, as large crustal masses influence the underlying flow of molten rock. The thermal insulation provided by thick continental crust creates temperature anomalies that deflect convective cells and gradually steer the overlying landmasses towards zones of convergence. This process exhibits a fundamental asymmetry where smaller continental fragments move preferentially toward larger, more stable masses, creating a natural hierarchy that governs the sequence and timing of collision events. The approach phase of continental collision spans geological epochs, during which the intervening oceanic crust gradually disappears through subduction and thermal recycling. The oceanic basins that separate converging continental masses undergo systematic narrowing as new oceanic crust formation fails to keep pace with destruction at convergent margins. This imbalance between creation and destruction of oceanic crust represents one of the most fundamental expressions of the planet's thermal evolution, reflecting the gradual cooling that reduces the efficiency of mid-ocean ridge volcanism. The first measurable effects of approaching collision appear in the deformation patterns developed within the converging continental masses themselves. The far-field stresses transmitted through the oceanic crust begin to influence continental structure hundreds of millions of years before actual contact occurs. These early manifestations of convergent tectonics create broad zones of crustal thickening and magmatic activity that foreshadow the eventual collision while providing detailed records of the stress fields and thermal conditions that characterize approaching continental convergence. Scientists studying the structural geology of ancient collision zones find evidence of these prolonged approach phases preserved in the metamorphic and magmatic rocks that formed during the pre-collision period. The pressure-temperature conditions recorded by metamorphic mineral assemblages reveal the systematic increase in crustal thickness and thermal perturbation that occurred during the hundreds of millions of years leading up to actual continental contact. These metamorphic records provide detailed reconstructions of the thermal and mechanical evolution that characterizes continental convergence. The mystery of stress transmission across early oceanic basins involves understanding how mechanical forces generated at convergent plate boundaries could influence continental structure across ocean basins thousands of kilometers wide. Modern plate tectonic theory provides clear mechanisms for stress transmission through oceanic lithosphere. Yet the high temperatures and mechanical properties of early oceanic crust create conditions where conventional stress transmission mechanisms may have operated differently or less efficiently. Current research suggests that stress transmission during early continental convergence operated primarily through thermal and chemical effects rather than purely mechanical stress transfer. The thermal anomalies created by continental collision zones influenced mantle convection patterns across entire ocean basins, creating far-field effects that could influence continental structure without requiring direct mechanical coupling. These thermal stress transmission mechanisms represent a style of tectonic interaction that has no direct equivalent in modern geological processes. The irony of geological collision timing lies in the contrast between the extreme patience required for continental approach and the relatively rapid adjustments that occur once contact is established. The approach phase operates on timescales of hundreds of millions of years, yet the final stages of collision and suturing can be accomplished within tens of millions of years once the intervening oceanic crust has been eliminated. This temporal asymmetry reflects the fundamental difference between the slow processes that drive continental motion and the more rapid adjustments that occur once mechanical contact is established. The chemical consequences of prolonged continental approach extend far beyond the immediate collision zone to influence the composition and structure of entire continental masses. The thermal and mechanical perturbations associated with convergence create conditions favorable for extensive magmatic activity and crustal differentiation within both converging blocks. These pre-collision magmatic events establish chemical and structural patterns that will influence the collision process itself and determine many characteristics of the resulting mountain systems. The atmospheric and oceanic effects of shrinking ocean basins begin to create systematic changes in global circulation patterns that influence climate and environmental conditions across the entire planet. The progressive narrowing of oceanic seaways restricts the circulation of ocean currents and modifies atmospheric flow patterns in ways that create new climatic provinces and environmental gradients. These early examples of tectonically controlled climate change establish the fundamental relationships between continental configuration and global environmental conditions. The gravitational effects of approaching continental masses create systematic variations in ocean depth and sea level that influence sedimentary processes and the distribution of depositional environments. The flexural response of oceanic crust to the approaching continental loads creates broad zones of uplift and subsidence that channel sediment transport and create preferred sites for sediment accumulation. These gravitationally controlled topographic changes represent an additional mechanism through which continental convergence influences surface processes. The magnetic signature of approaching continental collision appears in the systematic changes in magnetic field, strength, and orientation that develop as large crustal masses converge. The interaction between the magnetic anomalies associated with individual continental blocks creates complex interference patterns that provide detailed information about the geometry and kinematics of the convergence process. These magnetic signatures represent some of the most direct evidence available for understanding the mechanics of early continental collision. The development of primitive subduction zones along the margins of converging continental masses creates the first systematic recycling of oceanic crust back into the mantle. These early subduction systems establish the fundamental processes of oceanic lithosphere destruction that will become essential to plate tectonic cycling throughout Earth's subsequent history. The chemical and thermal effects of early subduction create distinctive magmatic and metamorphic signatures that provide detailed records of the conditions and processes that characterize oceanic crust recycling. The seismic activity associated with continental approach creates the first systematic patterns of earthquake generation and energy release that will become characteristic of convergent tectonic boundaries. The mechanical stresses developed during continental convergence generate earthquake activity across broad zones that extend hundreds of kilometers from the actual collision boundary. These early seismic patterns establish the fundamental relationships between tectonic stress and earthquake generation that will continue to operate throughout subsequent geological history. The timing of continental collision events appears to be controlled by the complex interplay between mantle convection patterns, continental thermal structure, and the mechanical properties of intervening oceanic crust. The convergence rate varies systematically during the approach phase, accelerating as the intervening ocean basin narrows and thermal effects become more pronounced. This temporal evolution of convergence rates creates distinctive patterns in the geological record that provide constraints on the dynamics of early tectonic processes. The influence of continental collision on global volcanic activity creates systematic changes in the distribution and intensity of magmatic processes across the entire planet. The thermal perturbations associated with collision zones influence mantle convection patterns on global scales, creating far-field effects on volcanic activity that extend far beyond the immediate collision zone. These global volcanic responses to regional tectonic events demonstrate the interconnected nature of Earth's internal processes and establish patterns that will characterize tectonically controlled volcanism throughout subsequent periods. Only took hundreds of millions of years to discover that continental collision required more than just bringing land masses together. It demanded the development of sophisticated mechanisms for stress transmission, thermal adjustment, and mechanical accommodation across planetary scale distances. Only required the planet to learn that collision represents a process rather than an event, involving complex sequences of preparation, approach, contact, and adjustment that span multiple geological epochs. The eventual mastery of continental collision will make possible the formation of supercontinents and the development of modern-style plate tectonics. But for now, these patient approaches represent the first experiments in large-scale tectonic organization. When supercontinents dreamed, the first supercontinent, Kenorland, begins assembling as scattered landmasses converge with the determination of gravity orchestrating a planetary waltz. This is not the familiar supercontinent of Pangaea that will capture human imagination billions of years in the future, but a more primitive assemblage, a tentative experiment in continental organization that operates according to principles the planet is still learning to master. The name Kenorland derives from the Kenoran orogeny, one of the earliest mountain-building events preserved in the geological record. Yet the supercontinent itself represents something far more significant than a single episode of crustal deformation. The assembly process unfolds through the systematic convergence of continental fragments that have achieved sufficient size and stability to resist recycling back into the mantle. These protocontinents approach each other across shrinking ocean basins with velocities measured in centimeters per year, rates so slow that the journey from initial convergence to final collision spans hundreds of millions of years. Yet the patience of geological time allows even these glacial movements to accomplish transformations that reshape the entire planetary surface. The configuration of Kenorland differs fundamentally from later supercontinents due to the unique thermal and chemical conditions that characterize early Earth. The constituent continental masses remain smaller and less chemically evolved than the cratons that will form later supercontinents, creating an assemblage that exhibits greater structural and compositional diversity. The suture zones between individual continental fragments preserve evidence of collision processes that operated under thermal conditions so extreme that they have no direct equivalent in later geological periods. The thermal effects of supercontinent assembly create the first systematic modifications of global mantle convection patterns, establishing feedback relationships between surface tectonics and deep Earth processes that will persist throughout subsequent geological history. The thermal insulation provided by the assembled continental mass creates a large-scale temperature anomaly in the underlying mantle that influences convection cells across the entire planet. This thermal blanketing effect concentrates heat flow in the continental region while reducing heat loss in surrounding oceanic areas. Scientists studying the remnants of ancient supercontinents find evidence of Kenorland's existence preserved in the structural patterns and geochronological signatures of Archean cratons distributed across multiple modern continents. The matching ages and structural trends observed in widely separated cratonic regions provide compelling evidence for their original proximity within a single large continental mass. Paleomagnetic analysis of ancient rocks reveals consistent magnetic field orientations that support reconstructions of supercontinent configuration and subsequent dispersal. The mystery of supercontinent stability during this early period involves understanding how large continental assemblages could maintain structural integrity under the extreme thermal conditions that characterized Archean surface environments. Modern supercontinents depend on the mechanical strength of cool, thick lithosphere to resist the forces that promote continental breakup. Yet early Earth thermal conditions created environments where even thick continental crust remained at elevated temperatures that reduced mechanical strength. Current models suggest that early supercontinent stability operated through different mechanisms than those that govern later continental assemblages. The high thermal gradients and elevated ductility of early continental crust may have actually enhanced supercontinent stability by allowing continuous mechanical adjustment to stress without brittle failure. This thermal weakening paradoxically created continental assemblages that were more resistant to catastrophic breakup while remaining susceptible to gradual modification and reorganization. The irony of Kenorland's existence lies in its simultaneous primitiveness and sophistication. The individual continental fragments that comprise the supercontinent remain small and structurally simple compared to later cratons. Yet their successful assembly into a coherent continental mass requires the operation of tectonic processes that rival modern plate tectonics in their complexity and efficiency. This early demonstration of large-scale tectonic organization establishes many of the fundamental principles that will govern continental behavior throughout subsequent geological periods. The atmospheric effects of supercontinent formation create the first systematic modifications of global circulation patterns that influence climate and environmental conditions on planetary scales. The presence of a large continental mass concentrated in one region of the planet creates distinctive atmospheric circulation patterns that differ fundamentally from the relatively uniform conditions that characterized earlier periods when continental masses remained small and widely distributed. The chemical evolution of Kenorland involves the development of increasingly complex crustal architecture as individual continental fragments undergo modification during the assembly process. The collision and suturing of separate continental masses creates opportunities for large-scale magmatic differentiation and chemical redistribution that would be impossible within individual continental fragments. These supercontinent-scale chemical processes establish patterns of crustal evolution that will become characteristic of all subsequent continental assemblages. The gravitational effects of supercontinent assembly create systematic variations in global sea level and oceanic depth distribution that influence sedimentary processes and the development of depositional environments. The isostatic effects of concentrating a large mass of buoyant continental crust in one region create complementary zones of uplift and subsidence that channel oceanic circulation and establish preferred sites for sediment accumulation. The magnetic signature of Kenorland appears in the systematic patterns of magnetic anomalies associated with the assembled continental mass and the distinctive magnetic field variations created by the concentration of magnetic minerals in continental crust. The magnetic effects of supercontinent assembly may have influenced the behavior of the global magnetic field and created regional variations in magnetic field strength that affected atmospheric chemistry and the distribution of charged particles. The development of supercontinent-scale hydrothermal systems creates the first large-scale networks of fluid circulation and chemical transport within continental crust. The thermal anomalies associated with supercontinent assembly drive extensive fluid flow systems that redistribute dissolved minerals and influence the mechanical and chemical properties of entire continental masses. These continent-scale hydrothermal networks represent a new level of geological organization that transcends the local and regional processes that characterized earlier periods. The biological implications of supercontinent formation remain largely theoretical during this early period. Yet the creation of large continental landmasses establishes environmental conditions that will become important for later biological evolution. The development of extensive continental drainage systems and the creation of diverse depositional environments associated with supercontinent margins begin to establish the geographical framework within which life will eventually evolve and diversify. The breakup mechanisms that will eventually disperse Kenorland begin operating almost immediately after supercontinent assembly, demonstrating the dynamic nature of large-scale tectonic systems. The thermal anomalies created by supercontinent assembly generate mantle plumes and hotspot systems that begin the thermal and mechanical processes that will eventually lead to continental rifting and dispersal. These early stages of supercontinent breakup establish the cyclical patterns of assembly and dispersal that will characterize supercontinent evolution throughout subsequent geological history. The timing of Kenorland assembly appears to coincide with fundamental changes in Earth's thermal and chemical evolution, suggesting that supercontinent formation represents both a consequence and a driver of planetary-scale evolution. The assembly of the first supercontinent marks a transition from the chaotic, relatively unorganized tectonic activity that characterized earlier periods to the more systematic, cyclic patterns of continental assembly and dispersal that will govern subsequent geological evolution. The influence of Kenorland on global volcanic activity creates systematic changes in the distribution and character of magmatic processes that affect the composition of the atmosphere and oceans. The thermal effects of supercontinent assembly concentrate volcanic activity in specific regions while reducing magmatic activity in others, creating global patterns of volcanic gas emissions and atmospheric modification that influence climate and environmental conditions across the entire planet. Only took over 1 billion years to figure out that making supercontinents required more than just assembling continental fragments. It demanded the development of sophisticated feedback relationships between surface tectonics, mantle convection, and global environmental systems. Only required the planet to learn that supercontinent formation represents a fundamental mode of geological organization that operates according to its own distinctive principles and timescales. The eventual mastery of supercontinent assembly and dispersal will establish the framework for all subsequent continental evolution. But for now, Kenorland represents the first successful experiment in planetary-scale continental organization. The weight of stone memory settles into the planet's depths as continental roots extend deep into the mantle, creating stable keels that will persist for billions of years like geological anchors holding the continents in place against the restless currents of deep Earth. These lithospheric roots represent one of the most remarkable achievements of early planetary evolution, the creation of mechanical structures so fundamentally stable that they will outlast the rise and fall of mountain ranges, the opening and closing of ocean basins, and the entire subsequent history of complex life on Earth. The process of root formation operates through the patient accumulation of buoyant crustal material and the thermal evolution of the underlying mantle, creating a form of geological permanence that approaches the timescales of planetary evolution itself. The formation of continental roots proceeds through the systematic cooling and chemical differentiation of the mantle material that underlies thickening continental crust. As continental masses achieve sufficient size and thermal insulation, the underlying mantle gradually cools and undergoes chemical modifications that increase its mechanical strength and reduce its density relative to the surrounding asthenosphere. This process creates a zone of chemically and mechanically distinct mantle material that becomes gravitationally and mechanically coupled to the overlying continental crust. The depth extent of these early continental roots reaches scales that dwarf the thickness of the continental crust itself. While the crustal portion of early continents rarely exceeds 40 or 50 kilometers in thickness, the associated mantle roots extend to depths of 200 kilometers or more, creating lithospheric keels that penetrate deep into the planet's interior. This extreme depth extent reflects the unique thermal and chemical conditions that characterized early Earth, where high heat flow and elevated temperatures created opportunities for extensive mantle modification that would be impossible under modern conditions. The chemical composition of continental roots differs systematically from normal mantle material through the selective removal of basaltic components and the concentration of more refractory, magnesium-rich minerals. This chemical depletion occurs through repeated episodes of partial melting that extract the more easily melted components while leaving behind a residue enriched in olivine, orthopyroxene, and other high-temperature minerals. The resulting root composition exhibits lower density and higher mechanical strength than normal mantle, creating the physical properties necessary for long-term stability. Scientists studying the structure of ancient continental roots rely primarily on seismic tomography and xenolith analysis to understand the formation and evolution of these deep crustal structures. Seismic wave velocities reveal the presence of high-velocity zones extending to great depths beneath ancient continental cores, while xenoliths brought to the surface by later volcanic activity provide direct samples of root material that preserve evidence of early formation processes. These studies reveal that many continental roots retain chemical and isotopic signatures that date to their formation during Archean supercontinent assembly. The mystery of root preservation involves understanding how relatively small differences in density and mechanical strength could create structures stable enough to resist recycling into the convecting mantle over billions of years. The density contrast between depleted root material and normal mantle amounts to only a few percent. Yet this modest difference proves sufficient to maintain gravitational stability against the forces that drive mantle convection and continental drift. Thermal modeling suggests that root preservation depends critically on the development of thermal boundary layers that insulate the roots from convective heat transport. The low thermal conductivity of depleted root material creates a thermal blanketing effect that maintains temperatures within the roots at levels significantly below those in the surrounding mantle. This thermal isolation reduces the tendency for convective erosion and helps maintain the chemical and mechanical properties that ensure long-term stability. The irony of continental root formation lies in the contrast between the violent, high-temperature processes that create them and the extraordinary stability they subsequently exhibit. The formation of roots requires extensive melting, chemical differentiation, and mechanical deformation under conditions so extreme that they represent some of the most energetic processes in all of geology. Yet, once formed, these same structures become among the most stable and long-lived features on the planet, exhibiting a geological inertia that persists across multiple supercontinent cycles. The gravitational effects of deep continental roots create systematic variations in the Earth's gravitational field that influence the behavior of overlying continental crust and the distribution of geological processes. The negative gravity anomalies associated with low-density root material affect the isostatic equilibrium of continental masses and influence the patterns of vertical motion and surface topography. These gravitational effects represent a form of deep crustal memory that influences surface processes long after the original root-forming events have ceased. The thermal evolution of continental roots creates distinctive patterns of heat flow and temperature distribution that affect all subsequent geological processes within continental regions. The thermal insulation provided by thick, low-conductivity root material concentrates radiogenic heat production within the continental crust while reducing heat flow from the deep mantle. This thermal architecture establishes temperature gradients and heat flow patterns that will influence magmatic activity, metamorphic processes, and hydrothermal circulation throughout the subsequent history of continental evolution. The magnetic properties of continental roots preserve detailed records of the magnetic field conditions and thermal evolution that characterize their formation. The magnetic minerals within root material record the intensity and orientation of ancient magnetic fields, while the thermal history of magnetic mineral assemblages provides constraints on the cooling rates and thermal evolution of deep continental structure. These magnetic records represent some of the oldest and most stable paleomagnetic signatures preserved on Earth. The mechanical properties of continental roots create zones of enhanced strength and rigidity that influence the response of continental crust to tectonic stresses. The high mechanical strength of root material provides a foundation that can support thick continental crust and resist the deformation forces that affect surface geological processes. This mechanical coupling between deep roots and surface crust creates a form of structural inheritance where ancient deep processes influence contemporary surface behavior. The chemical isolation of continental roots from mantle convection creates reservoirs of ancient mantle material that preserve chemical and isotopic signatures from early Earth history. The trace element and isotopic compositions of root material provide some of the most direct evidence available for understanding the chemical evolution of the early mantle and the processes that created chemical heterogeneity within the Earth's interior. These ancient chemical signatures represent geological time capsules that preserve information about planetary processes that operated billions of years ago. The interaction between continental roots and mantle convection creates distinctive patterns of mantle flow and thermal structure that affect global mantle dynamics. The presence of mechanically strong, chemically distinct root material deflects mantle convection patterns and creates preferred pathways for mantle flow that influence the distribution of volcanic activity and the behavior of tectonic processes. These deep structural effects demonstrate that continental evolution and mantle dynamics represent coupled systems that must be understood together. The biological implications of continental root formation remain largely indirect, yet the creation of stable continental platforms provides the geological foundation upon which complex surface environments can develop and evolve. The long-term stability provided by deep continental roots creates surface conditions that favor the development of extensive weathering profiles, sedimentary sequences, and eventually the complex biogeochemical systems that will support life. The influence of continental roots on global mantle convection creates systematic patterns of upwelling and downwelling that affect the distribution of heat flow and volcanic activity across the entire planet. The thermal and mechanical effects of root formation establish preferred sites for mantle plume generation and influence the pathways of mantle circulation in ways that create global patterns of geological activity. Only took hundreds of millions of years to figure out that making permanent continents required more than just building crustal masses. It demanded the development of deep structural foundations that could provide mechanical and thermal stability across geological timescales. Only required the planet to learn that continental evolution operates as a coupled system involving both surface processes and deep mantle modification, creating geological structures that span the entire depth range of the lithosphere. The eventual mastery of continental root formation will provide the stable platforms necessary for all subsequent continental evolution and surface environmental development. But for now, these deepening keels represent the first successful experiments in creating geological permanence. Breathing oceans between lands create narrow seaways that separate the assembled continental masses, establishing new patterns of water circulation that pulse with the rhythm of planetary rotation and thermal gradients. These are not the familiar oceanic basins that will characterize later geological periods, but restricted waterways that behave more like vast inland seas, bodies of water constrained by continental margins, yet connected to the global ocean system through passages so narrow that they create distinctive circulation patterns and chemical environments. The development of these intercontinental seaways represents a fundamental transition in Earth's surface organization, marking the emergence of complex geographical relationships between land and sea that will influence climate, ocean chemistry, and eventually biological evolution. The formation of restricted seaways occurs as continental assembly proceeds through partial convergence rather than complete collision, creating configurations where large continental masses remain separated by narrow oceanic passages. These seaways exhibit widths measured in hundreds rather than thousands of kilometers, creating water bodies that are simultaneously oceanic in their connection to global circulation systems, yet continental in their response to local climate and geological influences. The restricted geometry of these passages creates unique opportunities for the development of distinctive oceanographic and climatic conditions. The circulation patterns within intercontinental seaways operate according to principles that combine elements of both oceanic and lacustrine systems. The narrow width of these water bodies allows continental climate effects to influence water temperatures and chemical compositions across their entire extent, while their connection to the global ocean maintains exchange rates sufficient to prevent complete stagnation.
The resulting circulation patterns exhibit complex vertical and horizontal structure that reflects the interplay between local forcing and global oceanic constraints. The chemical evolution of seaway waters proceeds through the systematic modification of oceanic compositions by continental weathering inputs and restricted circulation patterns.
The high ratio of continental margin length to water volume creates conditions where continental chemical inputs dominate over oceanic exchanges, leading to the development of distinctive chemical signatures that differ systematically from open ocean compositions. These chemical modifications create the first systematic examples of continental influence on marine chemistry. Scientists studying the geochemical signatures preserved in ancient sedimentary sequences find evidence of these restricted seaway environments recorded in the isotopic compositions and trace element patterns of marine sediments deposited during periods of continental assembly. The distinctive chemical signatures of restricted circulation systems appear in the carbon, sulfur, and strontium isotopic compositions of ancient carbonate and evaporite deposits, providing detailed records of the oceanographic conditions that characterized early intercontinental seaways. The mystery of seaway circulation stability involves understanding how narrow oceanic passages could maintain sufficient water exchange to support distinctive marine environments without becoming completely isolated from global oceanic circulation. The balance between restriction and exchange represents a delicate equilibrium that depends on subtle relationships between seaway geometry, density stratification, and external forcing from tides, winds, and density gradients. Numerical modeling of ancient seaway circulation suggests that these systems operated in a regime intermediate between open oceanic circulation and closed basin dynamics. The restricted geometry created opportunities for strong density stratification and reduced vertical mixing, while tidal and density-driven exchanges maintain sufficient connection to global systems to prevent complete chemical isolation. These circulation characteristics created environments with distinctive chemical and physical properties that have no direct equivalent in modern oceanic systems. The irony of intercontinental seaways lies in their simultaneous restriction and global significance. These narrow water bodies represent some of the most geographically constrained oceanic environments on early Earth, yet their distinctive circulation patterns and chemical evolution influenced atmospheric and climatic conditions across much larger geographical scales. The chemical modifications that occurred within restricted seaways affected global oceanic chemistry through exchange processes that operated over geological timescales. The atmospheric effects of seaway formation create the first systematic patterns of continental-scale moisture transport and precipitation that differ fundamentally from the relatively uniform climatic conditions that characterized earlier periods. The evaporation from restricted water bodies creates localized sources of atmospheric moisture that interact with continental topography to generate precipitation patterns and atmospheric circulation systems. These early examples of land-sea climate interaction establish many of the fundamental principles that will govern continental climate systems throughout subsequent geological periods. The sedimentary processes within intercontinental seaways create distinctive depositional environments that preserve detailed records of the chemical, physical, and biological conditions that characterize these early marine systems. The restricted circulation patterns promote the development of density-stratified water columns that create opportunities for the preservation of organic matter and the formation of distinctive sedimentary facies. These early examples of restricted marine sedimentation establish depositional models that will become important for understanding ancient environmental conditions. The biological implications of seaway formation remain largely theoretical during this early period. Yet the creation of diverse marine environments with distinctive chemical and physical properties establishes the environmental framework within which marine life will eventually evolve. The chemical gradients and circulation patterns associated with restricted seaways create opportunities for ecological differentiation and evolutionary innovation that would be impossible in more uniform oceanic environments. The tidal dynamics within narrow seaways create distinctive patterns of water movement and energy dissipation that differ fundamentally from open ocean tidal systems. The restricted geometry amplifies tidal ranges and creates complex patterns of tidal resonance that generate strong currents and mixing processes. These enhanced tidal effects create physical environments that promote chemical exchange and sediment transport while maintaining the overall restricted character of seaway circulation. The thermal evolution of seaway waters exhibits distinctive seasonal and longer-term patterns that reflect their intermediate character between oceanic and continental water bodies. The restricted volume and continental influence create temperature variations that are more extreme than typical oceanic systems, yet more moderated than purely continental lakes. These thermal characteristics create density stratification patterns and convective processes that influence chemical evolution and circulation dynamics. The magnetic properties of sediments deposited within intercontinental seaways preserve detailed records of the magnetic field conditions and environmental changes that characterize these early marine systems. The distinctive sedimentary environments associated with restricted circulation create opportunities for enhanced preservation of magnetic minerals and detailed recording of paleomagnetic field variations. These magnetic records provide some of the most complete and high-resolution paleomagnetic data available from early Earth history. The influence of seaway formation on global oceanic circulation creates systematic modifications of deep water formation and thermohaline circulation patterns that affect climate and chemical cycling across the entire planet. The restricted exchange between seaways and open ocean systems creates opportunities for the development of distinctive water mass properties that influence global circulation when these waters eventually mix with open ocean systems. The geochemical evolution of seaway systems creates the first systematic examples of marine chemical cycling that operates on timescales, intermediate between rapid oceanic mixing and long-term geological processes. The restricted circulation within seaways creates residence times for dissolved chemical species that are long enough to allow significant biogeochemical modification, yet short enough to maintain chemical exchange with global systems. The structural geology of seaway margins creates distinctive patterns of continental deformation and magmatic activity that reflect the unique stress fields associated with partial continental convergence. The maintenance of narrow oceanic passages between converging continental masses requires the operation of extensional processes that counteract regional compression, creating complex patterns of crustal deformation and volcanic activity along seaway margins. Only took hundreds of millions of years to figure out that continental assembly required more than just bringing land masses together. It demanded the development of sophisticated geographical arrangements that could maintain oceanic connections while creating continental-scale environmental systems. Only required the planet to learn that the relationship between land and sea represents a dynamic balance that creates opportunities for environmental innovation and chemical evolution. The eventual development of complex seaway systems will provide the geographical framework for oceanic and atmospheric circulation patterns that will influence global climate throughout subsequent geological periods. But for now, these breathing oceans represent the first experiments in continental-scale geographical organization. The slow waltz continues as tectonic forces begin pulling the supercontinent apart, initiating cycles that will repeat throughout Earth's history with the persistence of a planetary heartbeat. This is not the catastrophic breakup that might be expected from such a massive geological undertaking, but a gradual process of thermal and mechanical adjustment that unfolds over hundreds of millions of years, a continental divorce negotiated through the patient language of rising mantle plumes, thermal doming, and the systematic development of rift systems that will eventually become new ocean basins. The breakup of Knorrland establishes the fundamental template for supercontinent cycling that will govern continental evolution for the remainder of Earth's history. The initiation of continental rifting begins almost immediately after supercontinent assembly, driven by the thermal anomalies created by the concentration of continental crust and the insulating effects of large landmasses on underlying mantle circulation. The thermal blanketing provided by the assembled supercontinent creates conditions favorable for the development of mantle plumes and hotspot systems that begin the thermal and mechanical processes leading to continental breakup. These thermal effects operate on timescales comparable to mantle convection itself, ensuring that supercontinent breakup represents an inevitable consequence of supercontinent assembly. The earliest stages of continental rifting manifest through the development of broad zones of thermal uplift and crustal extension that create the first systematic patterns of intracontinental deformation. These early rift systems exhibit geometries and structural characteristics that reflect the mechanical properties and thermal structure of Archean continental crust, creating rift architectures that differ systematically from those that will characterize later geological periods. The high thermal gradients and elevated ductility of early continental crust promote the development of wide, diffuse rift zones rather than the narrow, sharply defined rifts that characterize continental breakup under cooler conditions. The magmatic processes associated with early continental rifting create distinctive volcanic rock types and igneous associations that preserve detailed records of the chemical and thermal conditions that characterized supercontinent breakup. The partial melting of thermally perturbed mantle beneath developing rift systems produces magmas with distinctive chemical signatures that reflect both the composition of early mantle and the effects of continental crustal contamination. These early rift-related igneous rocks establish many of the fundamental geochemical characteristics that will become diagnostic of continental breakup throughout subsequent geological history. Scientists studying the remnants of ancient rift systems find evidence of Knorrland breakup preserved in the structural patterns and igneous associations of Paleoproterozoic geological terrains distributed across multiple modern continents. The systematic orientation of ancient rift structures and the matching geochemical signatures of associated igneous rocks provide compelling evidence for the geometry and timing of supercontinent dispersal. Geochronological analysis reveals that continental breakup occurred through a series of episodic rifting events that span several 100 million years. The mystery of supercontinent breakup timing involves understanding the complex feedback relationships between thermal evolution, mechanical stress, and magmatic processes that determine when and how continental rifting begins. The balance between the thermal effects that promote rifting and the mechanical strength that resists breakup creates a delicate equilibrium that determines the longevity of supercontinent assemblages and the timing of dispersal events. Current models suggest that supercontinent breakup operates through a combination of thermal and mechanical processes that create positive feedback loops leading to accelerating rifting and eventual continental separation. The thermal weakening associated with mantle plume activity reduces the mechanical strength of continental crust while increasing the driving forces for extension, creating conditions that promote rapid transition from stable continental configuration to active rifting and ocean basin formation. The irony of supercontinent cycling lies in the fact that the very processes that enable continental assembly also ensure eventual dispersal, creating a geological system that is inherently unstable yet persistently self-organizing. The thermal and mechanical forces that drive continental convergence and collision establish the conditions that will eventually drive continental rifting and dispersal, ensuring that supercontinent formation represents a temporary phase in an ongoing cycle of continental assembly and breakup. The atmospheric and climatic effects of continental breakup create systematic changes in global circulation patterns that influence environmental conditions across the entire planet. The progressive opening of new ocean basins and the development of seaways between dispersing continental fragments establish new pathways for oceanic and atmospheric circulation that create distinctive climatic provinces and environmental gradients. These early examples of tectonically controlled climate change demonstrate the fundamental relationships between continental configuration and global environmental systems. The development of new ocean basins through continental rifting creates opportunities for the evolution of distinctive oceanic crust compositions and structure that differ from the oceanic crust formed at traditional mid-ocean ridges. The magmatic processes associated with continental breakup involve the interaction between mantle-derived magmas and continental crustal material, creating hybrid igneous compositions and volcanic associations that preserve evidence of continent-ocean transition processes. The gravitational effects of continental dispersal create systematic changes in global sea level and the distribution of oceanic depth that influence sedimentary processes and the development of new depositional environments. The isostatic adjustments associated with continental rifting and the formation of new ocean basins establish regional patterns of uplift and subsidence that channel sediment transport and create preferred sites for sediment accumulation in the newly forming oceanic systems. The magnetic signature of continental breakup appears in the systematic patterns of magnetic anomalies associated with the formation of new oceanic crust and the development of distinctive magnetic field orientations within continental rift systems. The magnetic properties of igneous rocks formed during continental rifting preserve detailed records of magnetic field behavior during supercontinent dispersal, providing constraints on the timing and kinematics of breakup processes. The hydrothermal systems associated with continental rifting create extensive networks of fluid circulation and chemical transport that influence the chemical evolution of both continental and oceanic crust. The thermal anomalies and structural permeability associated with rift development drive large-scale hydrothermal circulation that redistributes dissolved minerals and establishes distinctive chemical signatures in both igneous and sedimentary rocks formed during continental breakup. The seismic activity associated with continental rifting creates distinctive patterns of earthquake generation and crustal deformation that reflect the mechanical processes involved in continental extension and ocean basin formation. The earthquake activity associated with early rift systems exhibits characteristics that differ systematically from modern continental rifting due to the elevated temperatures and mechanical properties of Archean crustal materials. The biological implications of continental dispersal remain largely theoretical during this early period, yet the creation of new oceanic environments and the development of diverse continental configurations establish the geographical and environmental framework within which life will eventually evolve and diversify. The environmental gradients and ecological opportunities associated with continental breakup create conditions that will become important for biological evolution and ecosystem development. The chemical evolution of newly formed ocean basins creates distinctive patterns of seawater composition and marine chemistry that reflect the unique conditions associated with continent-ocean transition environments. The interaction between continental weathering inputs and primitive oceanic circulation systems establishes chemical cycling processes that will become fundamental to marine geochemistry throughout subsequent geological periods. The timing of supercontinent cycling appears to be controlled by the thermal evolution of the planet and the changing efficiency of mantle convection processes that drive continental motion. The systematic decrease in planetary heat production through radiogenic decay creates secular changes in the vigor of mantle convection and the efficiency of continental assembly and dispersal processes, establishing long-term trends in supercontinent cycling that will persist throughout Earth's subsequent evolution. Only took several 100 million years to discover that making permanent continents required accepting their temporary arrangements, that continental stability paradoxically demanded continental mobility through systematic cycles of assembly and dispersal. Only required the planet to learn that supercontinent formation and breakup represent complementary processes that must operate together to maintain the dynamic equilibrium between continental and oceanic systems. The eventual mastery of supercontinent cycling will establish the framework for all subsequent continental evolution and the development of modern plate tectonic systems. But for now, this slow waltz represents the first successful experiment in large-scale geological cycling. Ancient shores remember, as fossil shorelines preserve evidence of rising and falling sea levels that correspond to the shifting positions of continents across the planet's surface. These are not the familiar coastal landscapes that will one day host complex ecosystems, but primitive boundary zones between land and sea, transitional environments where the fundamental processes of erosion, deposition, and chemical exchange begin their patient work of creating the sedimentary record that will preserve Earth's early history. The preservation of these ancient shorelines represents one of geology's most remarkable achievements, creating a detailed archive of environmental conditions and sea level changes that spans hundreds of millions of years of early planetary evolution. The formation of recognizable shorelines requires the establishment of stable sea levels and continental margins that can persist long enough for characteristic coastal processes to develop and leave their signatures in the geological record. This represents a fundamental transition from the chaotic, rapidly changing surface conditions that characterized earlier periods to more stable environmental systems where systematic patterns of erosion and deposition can operate over geologically significant timescales. The development of stable shorelines marks the beginning of modern-style sedimentary processes and the systematic preservation of environmental information. The morphology of early shorelines differs significantly from modern coastal systems due to the unique atmospheric, oceanic, and climatic conditions that characterize the Archean and early Proterozoic periods. The elevated atmospheric pressures and temperatures create coastal environments where conventional wave action and tidal processes operate under conditions that have no direct equivalent in modern systems. The resulting shoreline features exhibit distinctive geometries and sedimentary structures that reflect these extreme early Earth conditions. The sedimentary processes operating along ancient shorelines create distinctive depositional sequences that preserve detailed records of sea level fluctuations, climate variations, and the chemical evolution of early marine systems. The systematic alternation between marine and terrestrial depositional environments creates cyclical sedimentary patterns that provide some of the most complete and high-resolution records available of early Earth environmental conditions. These sedimentary cycles represent the planet's first experiments in systematic environmental recording. Scientists studying ancient shoreline deposits rely on detailed sedimentological and geochemical analysis to reconstruct the environmental conditions and processes that characterized early coastal systems. The grain size distributions, sedimentary structures, and chemical compositions of ancient coastal sediments provide constraints on wave energy, current strength, water chemistry, and climate conditions that prevailed during their deposition. These analyses reveal that early coastal environments exhibited many similarities to modern systems despite the extreme planetary conditions. The mystery of sea level stability during early Earth history involves understanding how systematic patterns of sea level change could develop and persist despite the extreme thermal and chemical conditions that characterized early atmospheric and oceanic systems. The preservation of well-defined shoreline sequences requires relatively stable sea levels over timescales of millions to tens of millions of years. Yet early Earth conditions might be expected to create highly variable and unstable oceanic systems. Current research suggests that early sea level stability operated through different mechanisms than those that control modern sea level variations. The high thermal inertia of the early oceanic system and the distinctive properties of early atmospheric systems may have created conditions where sea level changes were primarily controlled by tectonic and isostatic processes rather than the climatic and glacial effects that dominate modern sea level variations. These early sea level control mechanisms created opportunities for the development of stable coastal environments despite extreme planetary conditions. The irony of ancient shoreline preservation lies in the contrast between the extreme environmental conditions under which they formed and the remarkable completeness and detail of their preservation in the geological record. The high-energy coastal environments associated with extreme atmospheric and oceanic conditions might be expected to create chaotic, poorly preserved sedimentary sequences. Yet many ancient shoreline deposits exhibit exceptional preservation of fine-scale sedimentary structures and environmental indicators. The chemical evolution of ancient coastal environments creates distinctive geochemical signatures that preserve information about early atmospheric composition, oceanic chemistry, and weathering processes. The interaction between continental weathering inputs and marine chemical systems along ancient shorelines establishes chemical gradients and reaction zones that promote the formation of distinctive mineral assemblages and chemical precipitates. These chemical signatures provide some of the most direct evidence available for understanding early Earth surface chemistry. The biological implications of stable shoreline development remain largely theoretical during this early period. Yet the creation of systematic coastal environments establishes the geographical and chemical framework within which early life will eventually evolve. The chemical gradients, energy sources, and environmental diversity associated with coastal systems create conditions that will become essential to biological evolution and the development of complex ecosystems. The tidal processes operating along early shorelines create distinctive patterns of sediment transport and deposition that reflect the unique properties of early atmospheric and oceanic systems. The high atmospheric density and distinctive oceanic circulation patterns create tidal ranges and current systems that differ systematically from modern coastal environments, leading to the development of distinctive sedimentary facies and depositional architectures. The wave energy systems associated with early coastal environments operate under atmospheric and oceanic conditions that create distinctive patterns of wave generation, propagation, and coastal interaction. The elevated atmospheric density and distinctive temperature gradients create wind systems and wave climates that differ fundamentally from modern coastal environments, leading to the development of unique coastal morphologies and sedimentary systems. The preservation potential of ancient shoreline deposits appears to be enhanced by the distinctive chemical and physical conditions that characterized early Earth surface environments. The elevated temperatures and chemical reactivity of early surface systems promote rapid mineral precipitation and cementation processes that enhance the preservation of fine-scale sedimentary structures and environmental indicators. The magnetic properties of ancient coastal sediments preserve detailed records of magnetic field behavior and environmental conditions during early Earth history. The systematic orientation of magnetic minerals in coastal sediments provides paleomagnetic information about ancient continental positions and magnetic field behavior, while the magnetic mineralogy preserves information about redox conditions and environmental chemistry. The isotopic signatures preserved in ancient shoreline deposits provide detailed records of early Earth atmospheric and oceanic chemistry that complement other geochemical indicators of environmental conditions. The carbon, sulfur, and oxygen isotopic compositions of ancient coastal carbonates and sulfates preserve information about atmospheric composition, biological activity, and oceanic chemistry that provides crucial constraints on early Earth environmental evolution. The structural geology of ancient coastal sequences preserves evidence of the tectonic and isostatic processes that controlled sea level variations and coastal evolution during early Earth history. The systematic patterns of deformation and uplift within coastal sedimentary sequences provide constraints on the rates and mechanisms of tectonic processes that influenced early continental evolution and environmental development. The diagenetic processes affecting ancient coastal sediments create distinctive patterns of mineral alteration and chemical modification that preserve information about early Earth fluid chemistry and subsurface conditions. The systematic changes in mineral assemblages and chemical compositions within buried coastal sequences provide insights into early Earth hydrothermal systems and subsurface chemical evolution. The correlation of ancient shoreline sequences across different continental regions provides evidence for the synchronous nature of sea level changes and environmental variations during early Earth history. The systematic patterns of coastal sequence development across widely separated geographical regions demonstrate that early Earth environmental systems operated on global scales and exhibited coordinated responses to planetary scale forcing mechanisms. The influence of ancient shoreline processes on global sedimentary cycling creates systematic patterns of erosion, transport, and deposition that begin to establish the fundamental relationships between continental weathering and marine sedimentation. The chemical and physical weathering processes operating in early coastal environments create the first systematic sources of terrigenous sediment and establish the land-to-sea transport pathways that will become essential to global biogeochemical cycling. Only took hundreds of millions of years to discover that making permanent geological records required more than just depositing sediments. It demanded the development of stable environmental systems that could operate systematically over geological timescales while preserving detailed information about environmental conditions and planetary evolution. Only required the planet to learn that shorelines represent fundamental transition zones where continental and oceanic processes interact to create distinctive environmental systems and exceptional preservation opportunities. The eventual mastery of systematic environmental recording will provide the detailed geological archives necessary for understanding planetary evolution and environmental change. But for now, these remembering shores represent the first successful experiments in systematic environmental documentation. The endless choreography settles into its eternal rhythm as continental drift discovers the patient cadence that will shape Earth's surface for the next 4 billion years, establishing patterns of movement and change that operate with the persistence of planetary time itself. This is not the conclusion of continental formation, but the beginning of a dance that will continue until the sun expands and the oceans boil away. A geological waltz so fundamental to planetary behavior that it will influence every aspect of Earth's subsequent evolution. The establishment of systematic continental drift represents the planet's graduation from chaotic experimentation to mature geological sophistication, marking the transition from learning basic processes to orchestrating complex, integrated systems that operate across multiple timescales simultaneously. The mechanics of mature continental drift operate through the elegant integration of thermal, mechanical, and chemical processes that create self-sustaining cycles of continental assembly and dispersal. The mantle convection systems that drive continental motion achieve a sophisticated balance between heat transport efficiency and mechanical coupling that allows systematic continental movement without the catastrophic instabilities that characterized earlier periods. This thermal and mechanical maturation represents the culmination of billions of years of planetary learning, creating geological systems that exhibit both stability and dynamism. The establishment of predictable continental drift patterns creates the first systematic relationships between continental configuration and global environmental conditions, establishing feedback loops that will govern climate evolution throughout Earth's subsequent history. The cyclic assembly and dispersal of continental masses creates systematic variations in oceanic circulation, atmospheric dynamics, and biogeochemical cycling that operate on timescales of hundreds of millions of years. These supercontinent cycles become one of the most fundamental organizing principles of Earth system evolution. The chemical consequences of systematic continental drift extend far beyond simple geographical rearrangement to influence the fundamental evolution of atmospheric composition, oceanic chemistry, and crustal structure. The cyclic processes of continental weathering, ocean basin formation, and crustal recycling establish global geochemical cycles that maintain planetary chemical balance while allowing systematic evolution of surface conditions. These chemical cycling processes represent sophisticated planetary metabolism that maintains habitability while enabling continued evolution. Scientists studying the long-term patterns of continental drift find evidence of systematic cyclicity preserved in the magnetic signatures, geochronological patterns, and structural relationships of ancient geological terrains. The matching of geological provinces across modern ocean basins and the systematic age progression of orogenic belts provide compelling evidence for the operation of systematic continental drift processes throughout the past 4 billion years. These geological correlations reveal that continental drift operates as a predictable, cyclic system rather than a random process. The mystery of continental drift sustainability involves understanding how the thermal and mechanical processes that drive continental motion can maintain their efficiency and systematic behavior over the vast timescales required for multiple supercontinent cycles. The gradual cooling of the planet and the systematic depletion of radiogenic heat sources might be expected to reduce the vigor of mantle convection and eventually shut down continental drift processes. Yet, geological evidence suggests that continental drift has operated continuously throughout Earth's history. Current models of long-term mantle evolution suggest that continental drift sustainability operates through complex feedback relationships between thermal evolution, chemical differentiation, and mechanical efficiency that maintain convective vigor despite overall planetary cooling. The systematic recycling of oceanic crust and the chemical evolution of mantle composition create conditions that can maintain convective efficiency and continental drift capability throughout geological time. The irony of mature continental drift lies in its combination of extreme complexity and apparent simplicity. The individual processes that drive continental motion involve sophisticated interactions between thermal, mechanical, and chemical systems that operate across vast ranges of spatial and temporal scales. Yet the overall patterns of continental drift exhibit simple, predictable geometric relationships that can be described by relatively straightforward kinematic models. This contrast between process complexity and pattern simplicity represents one of the most remarkable examples of geological self-organization. The atmospheric and climatic effects of systematic continental drift create the fundamental framework for long-term climate evolution and the development of habitable planetary conditions. The systematic variations in continental configuration create predictable patterns of climate change that operate on timescales comparable to biological evolution, establishing the environmental context within which life will evolve and diversify. These tectonically controlled climate variations become one of the primary drivers of evolutionary change and ecosystem development. The development of stable continental drift patterns creates opportunities for the evolution of complex biological systems that can adapt to systematic environmental change while maintaining long-term evolutionary continuity. The predictable patterns of continental assembly and dispersal create environmental gradients and geographical barriers that promote biological diversification while maintaining global connectivity that enables evolutionary innovation and adaptation. The magnetic signature of systematic continental drift creates the detailed paleomagnetic record that provides the primary evidence for understanding continental motion throughout geological history. The systematic recording of magnetic field orientations in rocks formed during continental drift creates a global database of magnetic information that enables detailed reconstruction of continental positions and motion histories. This magnetic record represents one of the most complete and systematic archives of planetary motion available in the solar system. The gravitational effects of continental drift create systematic variations in the Earth's gravitational field and rotational dynamics that influence atmospheric and oceanic circulation patterns on global scales. The redistribution of continental mass during supercontinent cycles creates changes in the planet's moment of inertia and gravitational potential that affect everything from ocean tides to atmospheric circulation patterns. The hydrothermal processes associated with systematic continental drift establish global networks of fluid circulation and chemical transport that become essential to maintaining planetary chemical balance and habitability. The systematic recycling of crustal material through continental drift processes creates opportunities for large-scale chemical exchange between surface and deep Earth reservoirs that maintain atmospheric composition and oceanic chemistry within habitable ranges. The seismic expression of continental drift creates the global patterns of earthquake activity and crustal deformation that provide the primary modern evidence for ongoing continental motion. The systematic distribution of earthquake activity along plate boundaries and the predictable patterns of crustal deformation associated with continental collision and rifting demonstrate that continental drift represents an ongoing, active process rather than a historical phenomenon. The biological implications of systematic continental drift extend throughout the subsequent history of life on Earth, creating the geographical and environmental context for biological evolution and ecosystem development. The systematic patterns of continental assembly and dispersal create opportunities for biological radiation and extinction that drive evolutionary innovation and adaptation throughout geological time. The influence of continental drift on global volcanic activity creates systematic patterns of magmatic processes that affect atmospheric composition and climate evolution throughout Earth's subsequent history. The systematic recycling of crustal material through continental drift processes establishes global patterns of volcanic gas emissions and magmatic heat release that influence atmospheric chemistry and planetary energy balance. The chemical evolution of continental drift processes creates increasingly sophisticated crustal compositions and structures that exhibit enhanced mechanical strength and chemical stability. The systematic differentiation and refinement of continental crust through multiple cycles of assembly and dispersal creates continental masses that become increasingly resistant to recycling and more capable of supporting complex surface environments. The timing relationships between continental drift and other planetary processes establish the fundamental chronological framework for understanding Earth system evolution throughout subsequent geological history. The systematic patterns of continental assembly and dispersal provide temporal markers and correlation tools that enable detailed reconstruction of planetary evolution and environmental change. Only took 4 billion years of patient experimentation to discover that making a habitable planet required more than just creating stable continents. It demanded the development of systematic continental motion that could maintain environmental diversity while enabling long-term stability and continued evolution. Only required the planet to learn that habitability represents a dynamic equilibrium that must be actively maintained through systematic geological processes operating across multiple timescales. The eventual mastery of continental drift will provide the geological foundation for all subsequent planetary evolution, creating the stable yet dynamic planetary system that will support the emergence and evolution of complex life. But for now, this endless choreography represents the culmination of the planet's geological education and the beginning of its mature operation as a complex, integrated Earth system. The dance slows now, settling into the deepest rhythms of geological time, where movement becomes so gradual it approaches stillness, yet never quite reaches rest. 4 billion years have passed since the first tentative experiments in continental formation, and the planet has learned to waltz with itself through cycles so vast they dwarf the imagination, each revolution taking hundreds of millions of years to complete. The continents drift with the patience of stone dreams, following currents in the mantle that flow like honey through the depths, carrying their ancient cargo of memory and possibility across the surface of a world that has finally learned the art of making things that last. In the quiet depths of the earth, the first continental roots maintain their vigil, anchored in the mantle like geological prayers that will persist until the end of time. These deep keels remember the Archean fires that forged them, preserving in their crystal lattices the chemical signatures of a young world learning to create permanence from chaos. They have become the stable foundation upon which all future geology will build, providing the mechanical strength and thermal isolation that makes complex surface processes possible. The oceans breathe between the continental masses with tidal rhythms that connect the immediate moment to the orbital mechanics of celestial bodies. While deep beneath the waves, the seafloor spreads with imperceptible persistence, creating new oceanic crust that will carry the magnetic memory of this moment toward distant subduction zones, where it will eventually return to the mantle's embrace. The cycle of creation and destruction continues its patient work, recycling the materials of the planet through processes so fundamental they operate like the circulatory system of a living world. Somewhere in the crystalline structure of an ancient zircon grain, the thermal memory of the first continental formation remains preserved, a microscopic time capsule that holds the temperature signature of processes that occurred when the Earth was young and learning to make solid ground. The grain tumbles through sedimentary cycles, surviving erosion and transport, burial and uplift, carrying its ancient message through billions of years of geological time, waiting for curious minds that will not exist for eons to decode the story it contains. The magnetic field embraces the planet with invisible arms, generated by the motion of molten iron in the core, connecting the deep interior to the space around Earth through lines of force that deflect cosmic radiation and create the aurora that will one day paint the skies with colors that no eyes yet exist to see. This planetary magnetism links the dance of continents to the cosmic environment, making Earth a participant in the larger choreography of the solar system, in the silence between tectonic pulses, in the stillness that separates one mountain-building episode from the next. The planet rests without sleeping, maintaining its slow circulation of heat and matter while the surface waits for the next phase of its endless transformation. Continental drift continues its patient work, carrying pieces of ancient Knorrland toward future configurations that will create new patterns of climate and circulation, new opportunities for complexity and change. The wind down of this ancient dance is not an ending, but a settling into the rhythm that will persist for billions of years to come. Each geological epoch adding its own movement to the choreography, while the fundamental patterns remain constant. The continents will continue their waltz across the planet's surface, assembling and dispersing in cycles that operate on timescales so vast they approach the eternal, yet remain grounded in the physics of heat and gravity and the patient chemistry of rock. Sleep comes to the geological world not as cessation, but as the deepest expression of its fundamental rhythms, where change moves so slowly it becomes a form of rest, and rest moves so persistently it becomes a form of change. In this geological sleep, the planet dreams of mountains yet to be born and oceans yet to form, while the ancient continental roots maintain their quiet vigil in the depths, holding steady the foundation of all future possibility.